Hi everyone, and last time we were looking at covariant derivatives and Christoffel symbols and some of their properties, just from quite a theoretical perspective. Now we're going to make it more concrete, and we're going to look at an example somewhat typical of the kind of thing you could be asked to do in a test or an exam. So we have this formula for finding Christoffel symbols here. Okay, so we showed that in the last video, and the Christoffel symbols are a property of your coordinate system. Okay, so if you choose a specific coordinate system, so spherical polar coordinates, or cylindrical polar coordinates, or elliptic cylinder coordinates, or whatever, the Christoffel symbols are just a fundamental property of that coordinate system. So a question can be something like this. You're given a coordinate system, so in our example here, it's 2D elliptic coordinates, and they're defined like this. So x equals cos mu cos nu, and y equals sine mu sine nu. So the elliptic coordinates are mu, which has to be a non-negative number, and nu, which is like an angle between 0 and 2 pi. And so we can be asked to find the Christoffel symbols, okay? So using this formula. Now this formula here, we need to know the metric tensor. Okay, so for the coordinate system, we need to know the components of the metric tensor. So here I have given you the expression for the line element in 2D elliptic coordinates. Okay, so ds squared equals sine squared mu plus sine squared nu times d mu squared plus d nu squared. And in a test or an exam, you could be just given that. So you could be given the line element, or you could be asked to find it from here. Okay, so remember in Cartesians, ds squared is just equal to dx squared plus dy squared. So you could be asked to use these transformations here from Cartesians to elliptic coordinates. So you could be asked in principle to find dx, dy, square them, add them. But at any rate, this is what you would get. So here we'll just take it as a given, and we will try to find some Christoffel symbols. So just for the sake of clarity of notation, let me call these coordinates mu and nu x1 and x2. Okay, so let x1 just be the same as mu, and x2 just be the same as nu. And so, what Christoffel symbols do we have? How many are there in principle to be found? Well, the Christoffel symbols that are to be found would be as follows. So you've got gamma, and remember the Christoffel symbol has got 3 indices, so 1 upstairs and 2 downstairs. So in the first instance, they could just all be 1. Then you could have a 1 upstairs, but 1 and 2 downstairs. But remember, it's symmetric in the lower 2 indices, so that's just the same as if you had 2, 1 at the bottom. Then there's also gamma, 1 upstairs and 2, 2 downstairs. And that's everything you can have with a 1 upstairs, if you think about it. And then you just have all the same ones again, except with the 2 up the stairs. So you would also have gamma 2, 1, 1, gamma 2, 1, 2, which is the same as gamma 2, 2, 1. Oops. And you could also have gamma 2, 2, 2, like so. So, in this video, I will not go through each and every one of them. Okay, so in principle, to find each of them, there are 6 independent ones here. So 1, 2, 3, 4, 5, 6. So you have to do this 6 times. Let me not do that here. So let me just pick a couple of them. I mean, the procedure is the same every time. So, to use this formula, we need the components of the metric. Now, what do we have? So remember, the components of the metric are just the coefficients of the squared differentials. So g u mu, or well, let me call it g11 to be consistent with this. So g11 will just be sine squared mu plus sine squared nu, And that will also be G22, because that's the same coefficient of d nu squared, so that's also G22. And the other components, so the off-diagonal components, so G12 and G21, they're equal because the metric tensor is always symmetric, but they're just 0. Okay, so we don't have a d mu, d nu mixed differential here. Okay, and because the metric is diagonal, that means it's easy to find the inverse metric. You simply take 1 over. So G11 will be the same as G22, both superscript, and it'll just be 1 over this thing. So it'll just be 1 over sine squared mu plus sine squared nu. Okay, so now that we've got our components of the metric, let's have a look at one of the Christoffel symbols. Okay, so let's take gamma, which one have I tried already? Gamma 1, 1, 2. Okay, so let's just use this formula. So what have we got? A half, and then G, and then K, which is the upstairs index on the Christoffel symbol, so that's 1. And then we have a dummy index A, which just stays as A. And then we have dg dx plus dg dx minus dg dx. And then on the last term, we are going to have ij, which is the coefficients of down here. So 1, 2, a, and then we have 1a, 2, and 2a, 1. Okay, so that's just plugging in the indices here with k equals 1, I equals 1, and j equals 2. Okay, so fine. Let's just plug in what everything is. Now, the slightly annoying thing is that we have that dummy index a. So in principle, we have to sum over that. So a can equal 1, or it can equal 2, and we have to do both of those and add them. But for a diagonal metric, it works out very nicely, because if you look here, you've got G1a, okay? And G1a is 0 if a equals 2. Okay, so I've written it here for the covariant metric tensor, but it's true for the contravariant as well. So G12 is equal to G21, which is 0. So in the sum over a, only the term with a equals 1 survives. So actually, this just becomes a half G11, and then dg, and then everywhere I have an a just becomes a 1. So 1, 1 dx2 plus dg21 by dx1 minus dg12 by dx1. And in fact, if we look carefully, we have even more stuff that becomes 0, because look at this term. Look here, G21, that's 0. So that term's gone. And look here, G12, that's 0. So actually, it simplifies down quite a lot. So we just have a half G11 dg11 by dx2. Okay, and now we can finally actually put in what that is. So we have a half G11 is 1 over sine squared mu plus sine squared nu, and then dg11 by dx2, that means differentiate this thing with respect to nu. Okay, so it's the derivative of this with respect to x2, which is nu, and that doesn't depend on nu, that's just sine squared mu, and so I will just have 2 sine nu cos nu. Okay, and the half cancels the 2, so in the end I just have sine nu cos nu divided by sine squared mu plus sine squared nu. Okay, and now let's do another one for good measure. So let's just do gamma 222, let's say. Okay, so again using this formula, that will be a half g, and then I, j and k all become 2, so you'll have 2a, and then you'll have dg dx plus dg dx minus dg dx, and this will be 2a, and then you'll have 2a2 and 2a2 again. Okay, and again there's a sum over a here because a is a dummy index, but the metric's diagonal, so you only get a non-zero contribution when a equals 2. Okay, because for a equals 1, we just have g21 equals 0. So this will just become a half g22, and then everywhere you have an a, it just becomes a 2. So dg22 by dx2 plus dg22 by dx2 minus dg22 by dx2. So turns out in the round brackets this time, those three partial derivatives are all the same. So you've got 1 plus another 1 and then minus 1. So this one cancels out this one, let's say. So you just have a half g22 dg22 by dx2. Okay, so what will that be now? So g22 superscript, so just be careful not to get mixed up with those. That's 1 over sine squared mu plus sine squared nu, and then multiplied by the derivative of g22 subscript, which is this. So the derivative of this with respect to x2, which is nu. Okay, so that bit turns out the same as in the last Christoffel symbol we found. So again, that'll be 2 sine nu cos nu. The half cancels the 2, and it turns out to be sine nu cos nu over sine squared mu plus sine squared nu again. Okay, so that's just an example of a typical kind of question where you're given a coordinate system and you're asked to find some Christoffel symbols for it. And you can see that though that could quickly become kind of tedious. Okay, so this is only a 2-dimensional coordinate system, and there are 6 independent Christoffel symbols to be calculated. So you have to do this thing 6 times to get them all. And you can imagine for a 3-dimensional coordinate system, you know, that's going to be much worse. It's going to be tedious. So what we're going to see in the next video is we're going to start looking at something called geodesics, and that will give us another way, yet another way, of finding Christoffel symbols for a particular coordinate system. Okay, so that'll give us 3 ways in total. So the first way was from the basis vectors, but that was awkward. The second way is using this formula, which avoids the basis vectors, so you just need the metric tensor. So it's less awkward, but still time consuming. The third way that we're going to see next day is by finding geodesics for the coordinate system, and the Christoffel symbols will kind of drop out, but more on that next time.